Thank you very much. So yesterday we introduced a couple of tools, and today we're going to get to business, and we will assume that f is reduced on a surface x. And the first definition I will give you is that of an f-exceptional curve on x. So what is an f-exceptional curve on x? Is a curve C. Verifying these two properties. So it's smooth and rational, and c squared is -1. And so either you've seen it last week or you already know it, or I'll tell you. There is, given by Castelnuovo's theorem, a birational morphism contracting C to a smooth point for x bar. And the second condition, so via this birational morphism, f defines a foliation f bar on x bar. And an f-exceptional curve is a -1 curve, such that this resulting foliation f bar is still reduced. Okay, so remark. So now we consider a blow up or a blow down, contracting C to a point. And we have also f and f bar. And we've seen yesterday that if P is not a singular point for f bar, then C is f invariant. And Z of fc is 1. So I didn't tell you this exactly in this language, but that's what we proved basically through some of the examples. And 2, if P is in the singular locus of f bar, then, so this is, again, via the local forms of reduced foliations. Again, we can prove that C is f invariant. And Z is 2. Here we saw just the easy example of x dy plus y dx. Okay. So in this first case, kf.c is -1. And in the second case, kf.c, so maybe I should do the computation, is chi of c plus z minus chi of c plus z. Yes, so this is -2 plus 2, 0. Okay. Very good. So another definition, we say that f is relatively minimal if there are no f-exceptional curves. Okay, and the theorem one can prove, well, we consider X with a foliation F, and we can find a birational morphism, mu, a sequence of blow-ups or blow-downs, such that the resulting F bar is relatively minimal. So how is this proved? We consider XF. We hunt for F exceptional curves. If we don't find any, then the foliation is relatively minimal. Otherwise, there is one, and we contract it. And we look at the following surface with the foliation, and we look for F exceptional curves. And if there are no, we are happy. Otherwise, we contract. And we have to stop because at each contraction, at each blowdown, the Betti numbers or the Picard number drops. OK? So this is exactly the same proof as a minimal model for surfaces. OK? Now I would like to open to parentheses. I need to introduce new language. So first one is on Zariski decomposition. OK, first of all, definition, a divisor, D is pseudo-effective if for every big divisor, D plus P is big. So this is a definition. So you've seen in yesterday's lecture by Simone what a big divisor is. And you've probably understood that it's a subtle notion. So if you're not familiar with big divisors, I will give you an equivalent definition, which is a theorem. And this is good for us for working. A theorem by Buxom, Demailly, Paun, and Peternel. And this is pseudo-effective. If and only if, for every ample divisor, we are on surfaces always. So D dot H is not negative. OK? And now maybe a couple of examples. I will often write Ceph or pseudo-effective. So examples of pseudo-effective divisors. The first one is the one of effective divisors. So an effective divisor is also Ceph. Okay, the intersection with an ample class is non-negative. And then we have Neff divisors. So Neff, just recall that Neff means having non-negative intersection with every curve. So in particular, we can find a multiple of every ample, which has a section. So this section, the zero locus is a curve. So maybe some examples of non-Ceph divisors. Well, if minus d is effective and d is non-zero, then d is not Psef. And now, since I don't want you to believe that, that either d is Psef or minus d is Psef, I will give you also an example there. We'll consider P1 cross P1, and Fi, the fiber of the projection onto the ith factor, and we'll take D, F1 minus F2. This is not Psef. And also minus D is not Psef. Okay? Just to have something in mind. Now, an important definition, it's also a theorem by Zariski and Fujita. So we consider D pseudo-effective divisor. Then we can find unique P and N Q divisors with the following properties. So first of all, D is P plus N. And then 2, P is an F. And N is effective. And 3, if we write N as the sum of its irreducible components with coefficients bi, then the intersection matrix so the intersection matrix of the support of N is negative definite. And then 4, the intersection product of P and every component of N is 0. Okay, and then the equality D equal P plus N is called Zariski decomposition. Of D. And P is called the positive part. And then the negative part. Okay, maybe some properties of remarks. So the first one is that whenever MP has integral coefficients, the sections of all the multiples of D are the same as the global sections of all the multiples of P. So P captures all the sections of N. And then 2, so by Gauert criterion, the support of N can be contracted. Okay, and well, just maybe more obvious remarks. If D is an F, by uniqueness, D equals P, and then also self-intersection of P is not negative. So maybe I should. I'm not sure this intersection matrix business is completely clear. Maybe I will just give you just intersection matrix. Let's say we have 2 curves. And then M is C1 squared, C1, C2. C1, C2, and C2 squared. So it's always a symmetric matrix. So it makes sense to define negative definite and positive definite. And so in this case, well, if we consider AC1 plus BC2, and self-intersection is linear algebra computation. Okay, so this is what we are going to use. The negative definite matrix means that every curve supported in the support of N has negative self-intersection. This is basically the most important thing we are going to use about that. Okay, so second parenthesis is about Separatrix theorems. So the classical Separatrix theorem states that through every point in the singular locus of a foliation, there is a separatrix. And the version we will need is Camacho's version of the separatrix theorem. So we consider C curve which is connected, let's say, F invariant, and with negative definite intersection matrix. And that's it. And then there is a point, P, in the curve, which does not belong to the singular locus of the curve. And a separatrix oh, maybe it does, but a separatrix through the point, not contained in C. Okay, so I will not prove the theorem. I will do a proof by drawing. So we have our curve C, and by Grauert criterion, we can contract the curve to a point. And then by the classical Separatrix theorem, maybe in a singular version, there is a Separatrix through P. And then we look at its strict transform, which is going to pass, I don't know, here. And this is the curve we were looking for. And so here we have two intersection points, and just remark that these guys, P1 and P2, are in the singular locus of F. So where two F invariant curves meet, there is a singular point for the foliation. Okay? So now we can go back to our foliations on surfaces. So we always are in the reduced case. And we look at KF, and we assume KF pseudo-effective. So tomorrow we're going to look at the non-pseudo-effective case. But if KF is pseudo-effective, then we consider its Zariski decomposition. And the goal for today is understanding n. So we assume that n is non-zero. That is, we assume that kf is non-nef. So there is C in X such that kf.c is negative. So how is this, what can we say about C? First thing we can ask is, can C be non-F invariant? So the only case we know so far is something I forgot. I erased, I think. Yes, so sorry, it's here. We've seen that if we blow up a smooth point for the foliation, we get a curve with -1 intersection with the canonical. And that one was F invariant. So can this happen? Can C be non-F invariant? So one of the few things we can do is, well, this has to be negative. But then if C is non-F invariant, then this is minus C squared plus the tangency. And so the tangency is always non-negative. And then we took our C with the negative intersection with KF, but then C is contained in N. Then, as we said, the intersection matrix of N is negative definite, so this is strictly positive. OK? So the answer is no. Just a remark. We just proved that in general, if C is non-F invariant, then this is going to be useful later on. This sum is non-negative. OK, so then C is F invariant. And we compute the intersection with our other adjunction formula. And now just remember that since F is reduced, this Z is non-negative, and Z is positive, well, Z is 0, if and only if C is contained in the smooth locus of F. So what are the possibilities for G and F in order for the intersection product to be negative? So we see straight away that G is 0. So C is a rational curve. And then Z can be 0 or 1. So, but again, can Z be 0? Can C be contained in the smooth locus for the foliation? What do you think? So again, our C is in the support of n, and then C squared is negative. So if Z is 0 and C is contained in the smooth locus, we contract it. And through P, there is no separatrix. So we get a contradiction with this separatrix theorem in Camacho's version. OK, so the only possibility is Z equal 1. And kf.c is -1. And now there is a fact I will not prove. So if C squared is -1, then C contracts to a smooth point for the foliation downstairs. So if f is relatively minimal, c squared must be smaller than -1. Okay, and this leads us to the next definition. Is that okay? Are there questions so far? So here's the Brook-Young chain. Is a curve C. Let's say it has n components with the following property. So when we intersect two components of C, the intersection is less or equal than -2. If I equals j, it's 1. If I is j minus 1 or j plus 1, and it's 0 otherwise. So this is a complicated way of saying that the components, well, there is a labeling of the components. Such that the curve is a chain, and every self-intersection is less than or equal to -2. Oh, okay. Maybe this is a good example for an interesting intersection matrix. So here we have just the self-intersections on the diagonal. And then we have ones on the under and upper diagonal, and 0 in every other. Thank you. Thank you. Yes, yes. Thank you so much. It's very important for, yeah. Thanks. Okay, very good. Okay, so now we are ready for a statement of our theorem of today. This is due to Macquillan. So we consider f relatively minimal. With kf self. Then the support of n is a disjoint union of ci's, where ci is a Hirzebruch. Well, let me write hj. The Hirzebruch-Young chain. CIs are f invariant. So once again, we have our curve, our chain C1 to Cm. And we look at the singularities of f intersected with Ci. Of course, every singular point of the curve is singular for the foliation. So this must contain the singularities of the curve. And then by the Separatrix theorem, since the intersection matrix of Hirzebruch-Jung chains is negative definite, we must have another singularity on the curve. And the other singularity is on one of the extremal curves. So OK, and so the Ci is maximal with the property. And moreover, if we write n as sum of its irreducible components with coefficients, then all the coefficients are strictly smaller than 1. OK, so this is the theorem. I'm sorry. It's, no. And I'm going to present you a proof by Brunella. And so not only this proof, but all the material of these lectures come from a beautiful book called Birational Geometry of Foliations. But there are other proofs. So just, of course, there is one in the equivalence paper, canonical models of foliations. So if you like treasure hunting, I strongly recommend to look at this proof, to look for the proof in the paper. So no, it's worth it. I promise it's really worth it. And then there is another one by Paolo Cascini. And it's in some notes, which are probably on the web page of the school. And this proof uses negativity lemma. It's a fundamental tool in birational geometry. But today we will do proof by Brunella. And OK. So first step. By the discussion above. So we are assuming that n is non-zero. And then we proved that there is at least one f-invariant curve with a self-intersection less than -1 and such that z of f is 1. So there is at least one chain of the type of the statement in n. And step 2 is kind of, can look like an artificial definition, but it's a smart trick. So we denote by C1 and CK the Hirzebruch-Jung chains, F invariant, and maximal inside the support of N. And my notation for the irreducible components will be Cij. So I can write my N as the sum of the part contained in the curly Ci's plus something else. Okay, and then I denote by T the sum of the irreducible components of the other part, which are not F invariant. Okay. And I will define some auxiliary indices and divisors, and then I will try to explain what they are. So first of all, I will.
Sorry.
Yes.
There is at least one chain.
So.
But that every invariant curve must be rational with negative self-intersection. Right?
So we assume that Kf is not F. So N is non-zero.
Yeah.
And there is a curve that has negative intersection with Kf. So we proved that it's that is F invariant. And we proved that Z is 1. So there is one singular point on the curve. One F singular point on the curve. OK? And then I told you that if the self-intersection of C is -1, then I can contract C to a smooth point, smooth always for the foliation downstairs. So if the self-intersection of C is -1, F is not relatively minimal.
Yeah.
Right? So the self-intersection is at least, well, is at most -2. And so C is C itself, it's a Hirzebruch-Jung chain.
How do you exclude the cycle? Maybe because there are two singular points on the curve.
Exactly. No, cycles appear in another theorem by McQuillan where you describe the zero locus
But
of
you
the
exclude
KF.
the cycles because otherwise there are two singular
Exactly.
points on the curves.
Those will never be a part of N. Yeah,
Okay.
yeah. That was the question.
Yeah, that was
Okay.
How do you exclude the cycles?
No. There are no cycles in the support of N. And in general, it's a tree. Because when you do further blow-ups, OK. Now, I'm sorry, I'm adding notation. It's not very fair, but I will say that the indices here go from 1 to Rj. And I will define capital R. This is the max of all the i's such that Cij intersection T is empty. So, OK. So let's say that we have our, we have our chain like this. Is 1, 2, and 4. And here there is the singular point. And then let's say that here we have T. So then here small r is 4 and capital R is 2 in this drawing. So Rj is the biggest, such that there is a chain which doesn't meet the non-F invariant part. Okay, and then we define these auxiliary coefficients, the minimum between these two numbers, where, so delta I is 2 up to R, and it's 1 for R. So this minimum is always, this B hat is always smaller or equal than 1 because this quotient is, and if we take the rth, this is smaller or equal than 1/2, because here we get 1, and the self-intersection is the self-intersection of Cij is smaller than -2. Okay, so what do we do with this divisor? Sorry, with these coefficients? We do divisor n bar is n. N minus this thing, which is supported on the chains, but has coefficients Bij hat. Okay. So why is this definition a good definition? So these B hats are defined in such a way that n bar plus t intersected with Cij, this is non-negative for every Cij in Cj. Now here the computation is not difficult. I will partly leave it as an exercise. So and there are basically 3 cases. I smaller than or equal than R, I equal Rj, sorry, Rj plus 1, and I bigger than Rj plus 1. I will do this one. Maybe we won't, because there is no time. But they are, so. This is very easy. This is slightly more interesting than this one, and this uses the Bij hat. And now, we assume, let's consider C in the support of N0, not F invariant. Okay, then we want to intersect it with n bar plus t. And now by definition of R, so here all the so this is a double sum. I goes from 1 to Rj. By definition of Rj, C, which is not F invariant, is inside T. So it doesn't meet this guy. So this is n plus t dot c. And now this intersection is at least n plus c dot C. And then again, C is inside the support of N. So it has 0 intersection with P. And it was one of the initial remarks that this guy is not negative. This is the tangency order. OK, so step 5. We want to prove that this guy is 0. If this is 0, then all the curves are F invariant, and N coincides with this guy. All right. So assume by contradiction that it is not 0. And then again, its support is inside the support of N. And this implies that the self-intersection is strictly negative. So the self-intersection is strictly negative. Therefore, we can find the curve C0 such that n bar plus t cross C0 times C0, sorry, is strictly negative. And so we've seen in step 3, I guess, that every curve in the chains has non-negative intersection with this n bar plus t. And we've seen in last one, step 4, that if C is not F invariant, then it has no negative intersection with this guy. So. OK. And now, so the remark is that C0 can meet a chain only along the last point of Ci. And OK, so here there are two cases. Oh, maybe Cj. So if Rj is strictly smaller than so if capital Rj is clearly smaller than Rj, then n bar cross C0 is exactly n bar times C0. And if they are the same, then maybe we have to subtract the b hat corresponding to the last curve of the chain. So here, And now remember that those B hat were at most 1/2. So what did we prove? Or maybe I should just continue here. Okay. Now let's go back to the initial inequality. It was this one. We add what we just found out. And then there is the T times C0. And on the other hand, okay. Okay. Now, see, we consider this inequality, so this piece less than 0, and so the point of the end of this proof is that we cook up two inequalities. I'm not sure what I can. Okay, let me try and do this. So, on one hand, we have this inequality. And on the other hand, n times C0 is Kf times C0. And this is minus chi plus Z plus T times C0. And so the important remark here is that Z Z is at least all those intersections, because all of those curves are F invariant. So wherever they meet, there is a singular point. So I'll skip some steps, but so putting all these inequalities together, we find magically that Z must be at most 3, and that this intersection product is strictly positive. And now we don't have many possibilities. So if Z is 1, then C0 is the head of a chain. But this is a contradiction with one of the steps, step 3. If Z is 2, then C0 meets either one chain or two chains. But if it meets just one chain, so this is C0, it means that the chain was not maximal. So this cannot happen. And if it meets two chains, well, let's say we have the two chains like this, then it can meet them along their singular points. And this gives a contradiction with the Separatrix theorem once again. In the case Z equal 3 is more or less the same game. There is a contradiction again with the Separatrix theorem. OK, so we proved that m bar plus t is 0. And the negative part is supported along these Hirzebruch-Jung chains. And the statement on the coefficients being smaller than 1. So say that n is, let's assume that we have just one chain. But the general case is completely analogous. And then those B1, BK, they are completely determined by the intersection matrix of the chain. And by the property that this intersection product has to be -1 and then 0, because those are kf.c1, kf.c2. So the coefficients are given by the inverse of this matrix, and with a bit of linear algebra, one can prove that the first column of the inverse of the matrix, which is the BIs, is made by smaller than 1 entries. So this is the end of the proof. Sorry if it was a little sketchy. That's the end of my talk too.